Hello viewers. Before I introduce my special guest tonight, I want to say a word about next week, because as you're aware, November the 3rd is the final day for voting in the American election. And we are scheduled for November the 4th. So it's possible by then that we will know who the winner is, Biden or Trump. It may not, because of course it depends on whether they finish counting the votes, and some of the states take a long time. And then of course there's the problem of the Electoral College, and who knows whether the loser will declare himself out. We'll have to wait and see. But I'm very pleased to announce, an ex-MEP coming on the show to analyze this situation and comment on the implications to the UK and the ROW, the rest of the world. Meanwhile, many of us knew that the dinosaurs were wiped out by an extinction. But how many of us knew that they were brought into existence by one? Well, I know one man who does. It's Professor Mike Benton. Hello, Mike.
Good evening. Hello.
How the devil are you?
Very well indeed, thank you.
Good, good, good. Now, you're at Bristol University, which I imagine is quite favorably placed for paleontology, being, within fairly easy reach of the Devon and Dorset coasts.
Yes, that's right.
A lot of early paleontology went on.
That's absolutely right. And everybody has heard of Mary Anning, who of course lived and worked in Lyme Regis 200 years ago. And in her day, she was bringing her discoveries to the attention of professional paleontologists in different parts of the country. But a lot of her specimens ended up in Bristol. We had a very active scientific and philosophical society in the 1820s, and they made sure to get a lot of her specimens.
Excellent. So, for the benefit of my audience and me, can you tell us, what is an extinction? I mean, I'm a retired science teacher, so I do know a little bit about geology, and so I can have a guess at what an extinction might be defined as. I'd say it's two strata in the geological timescale, the geological column, where there's a discontinuity. One layer contains some fossils, fossil type A, diversity, and the next layer contains different flora and fauna. Is that something like it?
That's about right. As a geologist, you have to be careful to check whether that shift is actually happening quickly, or whether there might be some missing time. Because in some rock successions, there may be a gap, there may be a complete change in the fossils, but it could represent, 100 million years missing time. But in most cases, as you described, that's what we find. And in fact, the early geologists began to notice that. And they were initially interested in fossils only for a utilitarian purpose, which was for dating the rocks. In a way, they didn't mind too much, or didn't think too much about why they might change. And so the big divisions of geological time, the Paleozoic, Mesozoic, and Cenozoic, those three are separated by big mass extinctions. And of course, the extinction event between the Mesozoic and Cenozoic, that's the famous one where the dinosaurs died out. And they noticed that discontinuity, as you describe it. You'd be collecting up through the rocks. If there were marine rocks, you would be finding ammonites and belemnites and the sort of fossils you can find on the Jurassic coast, indeed. And then at a certain level, they'd all gone. And if you're collecting on land, you'd be finding dinosaurs and other stuff like that. And again, they kind of stop at the same level. And then you find totally different things, mammals and modern kinds of creatures. We use the word extinction, of course. I think most people know that there are mass extinctions, which are these big events where lots of things go extinct at the same time. And the word extinction just means the end of a species. So there are millions of species on the Earth today. Each species has an average lifespan of maybe 1 million years, something like that, something between 500,000, 2 million. So it means extinction, individual species go extinct at any point. There's no predictability, and it may be if a species is on a particular location where the food supply runs out, it's stuck on an island, it's doing whatever it's doing, or indeed if human beings come along and do whatever they do, that species can go extinct. So extinct in that sense just means it's gone, it's disappeared. But geologists, paleontologists like myself, we're dead keen about mass extinctions. It's a sort of ghoulish interest, you might say, focusing on the end of things. And it's always the question people ask about dinosaurs, but I like the way you began this, because I think this is important. Yes, the extinction 66 million years ago that wiped out the dinosaurs and the ammonites and all these other creatures, that was bad news for those beasts. But if you wind back to the beginning of the dinosaurs, something like 230 million years ago, far, far back in time, there was another mass extinction there, or extinction event of some kind that we're talking about tonight. And it was bad news for a whole bunch of creatures, but it was good news for the dinosaurs, because it kind of cleared out the world and gave them a chance to come back, or at least to diversify and become established.
It's an ill wind, isn't it?
Quite. Somebody wins.
Yes. Now, you mentioned a couple of things there which I'd like to pick up on a bit, because I often get involved in debating with people on Facebook and Twitter and stuff, and they come to the platform not knowing anything, having a lot of misconceptions, and they expect me to teach them within, I don't know, 50 characters or something. So you mentioned that there's about 1 million species that are extant, and a lot of species have gone extinct. Well, I've heard different figures. How many species have gone? Is it 90%, 95%? What's happened?
If you mean in all of time, it is a huge number, of course, because the history of life is maybe 3.5 to 4 thousand million years. And so since the origin of life, it's almost impossible to estimate how many species have ever existed on the Earth. And of course, the loss of a species is tragic, but clearly over those long, long spans of time, they clearly have come and gone. And I think people are aware that up to the human era, of course, all of those extinctions we would call natural in some sense, because they're happening due to small-scale processes in some cases, like a bad drought or some particular climate event or some other thing, or larger catastrophes, a big eruption of a volcano, or who knows, whatever. Yeah, so I think people sometimes estimate that as many as 95 or maybe 99% of all species that have ever existed are now extinct, which is a figure I like as a paleontologist. It means that gives me a good scope of stuff to work on.
You're not going to run out of work. But the other thing you mentioned was that initially the geologists were looking at fossils with a view to using them for dating.
Yes.
Now, that gets accused of being like a circular argument, because you use the fossils to date the layers, and then you use the layers to date the fossils, or something of the sort. But of course, so I was going to say, since then we've got radiometric dating, which oddly confirms the original fossil estimates.
That was what I was going to say. It sounds circular the way you put it, and I think people, though, had confidence that it worked, and that at first, as I say, it was very utilitarian, so they weren't even thinking of that circularity, because people were just saying, here is ammonite A, which looks very different from ammonite B, And I find ammonite A always at this particular level in Dorset, and it seems to occur in the same kinds of rocks around Bristol and Bath, and the same in Yorkshire, maybe the same in South Germany. And A is always below B. You know, there's often a spatial relationship or something of that kind. They never go in reverse. And so the sequence, I think, tended to help. And the economic value of that at the time was because people were building canals, they were looking for coal. This was the basis of the Industrial Revolution more than 200 years ago. And I think up to the point where people started using fossils to date the rocks, wealthy landowners would go looking for coal almost at random. And they would say, oh, my neighbor 10 miles away has got a great coal deposit, maybe 10 feet under the earth. I'm going to dig 10 feet down under my estate. But if you didn't have an understanding of geology, you might be digging into granite or something completely ridiculous, or the rocks that you're starting on are older than the Carboniferous. All the coal in England pretty much is in the Carboniferous. So that was the sort of magic that the early geologists were able to do. They were able to say, just a minute, you know, I can tell you the age of the rocks at the surface. I can then predict what lies beneath. And it was that kind of predictability. But yes, the circularity, you're right. That's an easy argument that creationists and others might use and say, oh, well, the whole thing is buttoned up, you know. But it's like archaeological dating. You have multiple means of dating archaeological sites based on artifacts and written records, of course, radiocarbon dating now, and a whole bunch of other methods. And it's exactly the same for geology. We don't use radiocarbon dating, but we use other kinds of radiometric dating. And yes, as you said, lo and behold, they confirm. And there's other kinds of dating like magnetostratigraphy and all kinds of other instrumental methods which have got nothing to do with the fossils and no connection of any sort. They are independent and they all multiply confirm.
I'm glad you mentioned archaeology. We had an archaeologist on the show some months ago now, and he pointed out that it's just a case of who was buried first. And literally that, in a graveyard, you can date things by the body, the skeletons, one on top of the other.
Yeah.
A more gruesome way of doing it. Now, another problem that you mentioned creationists have is they think that the species are fixed. It's an easy mistake to make because we don't live long enough to watch big animals that are longer lived than us, maybe, or almost as long lived as us, and don't have a generation that is short enough time, lifespan. And we go to zoos and we go to farms and we see all these big animals and they don't appear to be changing.
Yeah.
But once you get into paleontology, you can see a progression. Yeah. And the fact of the matter is that species is it's a box that we force round organisms for our own convenience so that we can talk about them, and they don't really stay in it.
Yes, I think that's broadly right. And I think, though, they do have limits in the sense that all members of a species will share the same genotype. So the genetic material is, every individual has a different genome, but within a species there will be a great deal of shared material and common structure. And of course, through time, which is what we look at, we're very interested, as you say, in following a species through time. And that has been a difficult one to demonstrate. Certainly in the days of Darwin, it was quite difficult for him to put his hands on a really good example where you could follow huge collections, huge numbers. But the way people have done it now, I'll just give you an example where we tend to take examples where we're going back from the present day. So you start at the present day where you may have two species which are closely related, but they're sufficiently distinct that they can't interbreed and they keep apart and all the usual tests. And you can characterize them genetically. And people have done this particularly with planktonic organisms where the record is rich. Because and people often think, oh, that's a bit of a cheat. But I would say, no, it's not. Because these are species like any other. And there's no point trying to do this study with dinosaurs, for example. They're totally extinct, and you're lucky to find more than one specimen, so you can't even begin. And in order to study species, you need populations, you need large samples. And if you're studying planktonic organisms, of which there are great numbers, you can capture the modern examples, you can do the genetics, as I say, and then you can follow them. And because in the oceans, the sediment builds up on the deep sea floor very slowly, just millimeters per year or even per decade. Yes. You can take a meter or two of the sediment from the bottom of the ocean. You can do all the dating you can wish for using all kinds of isotopic means. And you've got enormous samples, and therefore people follow. And if you've got two closely related species, what people have found, you can track them back as they come together. You're doing it in reverse. And then they overlap, they overlap, they overlap, and you get to the point where you cannot discriminate those two populations.
Yes.
And there's a lot of good studies like that, and some of those show that in certain cases, species will split very fast, geologically speaking, i.e. within tens of years. Yeah. In other cases, they may take as much as 250,000 years to fully pull apart. So there's a lot of documentation now of this kind of thing. And if your creationist friend is willing to listen, is willing to look at the data, then you've got plenty of good cases to show.
Yes, yes. Of course, they even try to claim that humans have stopped evolving. But I read today that more babies are being born without wisdom teeth to erupt, for example, than previously. And of course, there was an interesting program, I think it was by Kat Arney, one of the Genius, spelled Gene, ES show she does on I think it's on, is it on the World program or Radio 4? And it was about lactose intolerance, which has evolved quite recently and many times over with slightly different variations. All interesting stuff. Anyway, you've got a presentation to show us, haven't you? Good. So if I'm
going to show you some evidence, yes.
If I screen this, and then I see that there are some questions coming in. So I'll screen this and I'll disappear and let you talk about it.
Thank you. So thank you very much, John. And the context of our conversation so far has been a paper that we published recently, which, if we could go to slide 2, is just published in Science Advances, and the title is Extinction and Dawn of the Modern World in the Carnian, Late Triassic. So let me just explain those various portions of the title. And then we're going to have an interesting little expose of how on earth can you lose a mass extinction, because we think we know it all, and yet we've only just hit on this. So you can see all the authors there. I'm kind of buried in there. And this was a review pulling together a great deal of information from many parts of the world, as you can divine from the different authors there, and based on many different branches of geology. But first of all, let me define what a mass extinction is, if we could move on to the next. And we often talk about, geologists often talk about the big 5 mass extinctions. And looking at this sequence with some helpful dinosaurs and other beasts, we start on the left in the Paleozoic and we run through to the present day on the right. And this graph is showing the extinction rate, which is the percentage extinction. And the high point in the middle is at the end of the Permian and the beginning of the Triassic. So that's the big one. And that's a 50% extinction rate of major groups. And that equates to something like 90% of species going extinct. And the extinction of the dinosaurs is between the Mesozoic and Cenozoic. That's the famous end Cretaceous mass extinction, which we may talk about later, probably caused by a big meteorite impact. And that marks the end of the dinosaurs and lots of others. And the event we're talking about is highlighted as the Carnian pluvial episode, a little purple blip. So the point I want to make here is there are many events through the last 500–600 million years of Earth history, when we talk about the big five, we're not delving into the Precambrian. So the whole chunk of time off to the left, which would disappear several meters off your screen and through into the next room, is the early history of the Earth, which we just call the Precambrian, which is a very Victorian name. It just means it's everything older than the Cambrian. And we know a lot more about it now than we did in Darwin's day, but we still kind of use that rather dismissive term as if to say this is just too ancient to be bothered with. And the big five are occurring at the end of the Ordovician, the end of the Devonian, the end of the Permian, the end of the Triassic, and the end of the Cretaceous. And indeed, they do tend to mark the end of divisions of time. So it's still a moot point whether this event I'm talking about classifies as big as any of the big five, or is it in a sort of medium category? But I think most people would accept it is an extinction event of some kind. So if we move on the claims, I just want to talk about briefly what we're saying. And this has got a fair amount of technicality in it, but I'll just touch on a couple of points that we may develop a little bit later, particularly to do with the killing model. How do we study? How do we determine what is killing? So we've got the date there, 233 to 232 million years ago. This is then the date we would say marking this big punctuation in the history of the Earth, the history of life, after which the dinosaurs become important. The second point is eruption of the Wrangellia LIP. What on earth does that mean? Wrangellia is a name of an ancient landmass associated with Western Canada. And there's a great deal of volcanic rock, basalt, along the far west coast of Canada and up to Alaska. And those are the remnants of this big phase of volcanic eruptions that were happening at that time. LIP stands for Large Igneous Province. Basalt is a kind of igneous rock. And the consequences of the eruption were pulses of high temperature, so global warming, associated with elevated rainfall, because the structure of the continents meant that as you raise the temperature around the tropics, it increases monsoon-type rainfall. There is a great deal of evidence of humidity happening, followed by sharp aridity. So the humidity isn't the killer. It's probably the aridity that follows. In a rough estimate, we came up with a loss of maybe 33% of marine genera, equivalent to 50% of marine species. But that's got a question mark because that's something that we still need to try to pin down. Probably a similar rate of extinction on land, but that's much harder to estimate, but still we'll look for that. Explosion of the dinosaurs happened afterwards. Also, origins of lots of modern groups, turtles, lizards, crocodiles, etc., and in the ocean. Massive change in the plankton, the reefs, and the so-called modern oceanic carbonate factory. The whole nature of carbon cycling in the ocean changed. Probably that's the more profound thing than the origin of dinosaurs, but in a way people care about dinosaurs. They don't care about the carbon cycle very much. So next one, please. Older and older dinosaurs. And so this is, again, quite detailed, but we won't worry about too much of that. Just to indicate that in the last, so this is beginning to look at the question of why did we miss this thing? Because as we discussed at the beginning, people, geologists and others have been identifying mass extinctions of one sort or another for 200 years or more. So why on earth did we miss this? Well, partly there's been a big revision of our knowledge of the fossil record of early dinosaurs in the Triassic period. And so where I've marked body fossils, those are the oldest skeletons, and they come from the Ischigualasto Formation in Argentina. But a number of years ago, some fossil tracks were found of dinosaurs in much older rocks. And there's a variety of other evidence which is drawing the origin of dinosaurs maybe 20 million years back in time, and is drawing it back into the early Triassic, which is the time of recovery from the end Permian mass extinction. And during that time, there was the radiation of various major groups of terrestrial animals, including the ancestors of dinosaurs. So if we could go on to the next slide, please. And there the extinction itself. So in a prescient way, you know, I have the advantage of considerable age. And it's quite nice to be able to cherry pick from what you did as a foolish youth, those things that you got right, and the things you got wrong, you just try to forget about. And so in 1986, I published this paper in Nature, more than one event in the late Triassic mass extinction. And indeed, that was pointing to this earlier event, what we now call the Carnian pluvial episode. But I had very little evidence. It was based on some rather poor analyses, but the best one could do at the time. So could we move to the next one? And in the next slide, talking about humidity, two colleagues here, Mike Sims and Alistair Ruffle, their portraits are there. They also, in a very prescient way, pointed to, they were aware of what I'd done, and 2 or 3 years later, they noted that there was a humid episode, meaning high rainfall, and they had ever happening. Next one, please. But this is unusual. In 1994, a team of paleontologists, quite distinguished paleontologists, and we were just cheeky young chappies at the time, published a paper, which I've never seen this sort of thing before, entitled very clearly, "A Rejection of a Carnian Pluvial Event in Europe." So normally if you get it wrong in science, but it's sort of not hurting anybody, people just quietly say nothing and just let it go. They might speak to each other and say, "Did you read that ridiculous paper? What a load of nonsense." But in medicine, it's different, of course. If you make big mistakes, they could have dangerous consequences. But in paleontology, the consequences are not usually very dangerous. So it was quite hurtful and unusual that this paper was published. And so we felt like very naughty boys. And therefore, we kind of shut up and thought, right, we better not say anything more about this. So next one, please. So this is part of the reason why, the data were not that great. They were, the geological data from Sims and Ruffle were restricted mainly to Europe. And therefore, it was easy for Vischer and others to say this is not global. If you're claiming an extinction event, it has to be global. However, apart from that, lots of changes in the technology of how we do the earth sciences were happening. And one of these was the further and massive improvement in dating techniques, including magnetostratigraphy. And so magnetostratigraphy refers to the fact that, as many people know, the north and south poles frequently, in geological terms, flip. And so what was north becomes south, and what was south becomes north. And it's not fully understood what actually happens to the Earth when the poles flip. And in fact, people think that may be about to happen now, because the strength of the Earth's pole, the Earth is like a great magnet, a bar magnet running from north to south. And the Van Allen belts in the atmosphere are part of that magnetic field, etc., etc. Nonetheless, what was happening during the late Triassic, if you look at this diagram, you've got all the purple stuff, and then look at that black and white Barber's pole labeled geomagnetic polarity. There were lots of reversals happening during this time interval, and the relative thicknesses correspond to time. And therefore, if you record this by geophysical means through long successions of rock, whether the rock is deposited on land or in the ocean, it doesn't matter. They will reveal aspects of this magnetic reversal timescale. And then you can kind of match them up. You've got a standard, you can take your section and see, slide it up and down, where does it fit? This allows us to correlate then from land to ocean. Next, please. And the other change that was happening was that people were looking in other parts of the world. And Sims and Ruffle again, 2016, wrote a review saying, actually, Vischer et al., you were wrong. And in fact, we were wrong. It's not just Europe, it's all these other continents. And they were able to publish this map. And I can use the map to explain a couple of other things briefly, but their key point was it's global. So they were able to smile a little bit and say, we got it right in 1989. But the evidence now has improved. The two things I can show and remind you of, first of all, is look at the layout of the continents, very different from today. Just by the by, at that time, all the continents were together as a supercontinent that we call Pangaea. And in the lower one, you can see the location of the Wrangellia large igneous province right up at the top left-hand corner. That's close to where Canada will become. And the other point about this is it shows something about the movement of air and climate across this single supercontinent. And this is to remind you that most rainfall comes off the ocean and it tends to fall fairly close to the coast. Living on an island like the UK, then of course we get rain everywhere. But if you have a large continent like Asia or Africa or South America, or indeed North America, you tend to, and Australia, you get a big desert in the center of the continent. So in the Triassic, most of the landmass was devoid of rainfall or had very little rainfall, except when temperatures went up sharply in the Carnian, and that drove the air masses across the land and gave an increase in rainfall, which was this whole humidity thing. So next, please. And then when we move on, here's the Wrangellia Basalts. I won't bang on about this too much. The map is there, the detail of dating. And this is really, in the bottom corner, there's a sort of flow chart. You can see there's a big volcano in the background. And I'll just talk you through two things that are happening. One is that when a volcano erupts, we don't care too much about the lava because that just affects things locally. We care about the gas. And the gases that come out of the volcano can go worldwide. And we know this from human records of, for example, the eruption of Krakatoa in 1883 was detectable worldwide. And in fact, changed the climate in Europe, even though the eruption happened on the other side of the world in Indonesia. So first of all, the gases that come out include carbon dioxide, sulfur dioxides, methane, water vapor. The sulfur dioxides give you a sharp cooling, but that's very transient and they disperse very quickly after a day or two. But the carbon dioxide, methane, and water vapor, these are greenhouse gases and they are pumped out in great volumes and they can have a global effect if the eruption is big enough. So you get warming of the atmosphere and that gives you warming of the ocean. And even though it's estimated that the warming was only maybe 5 or 6 degrees C, that's actually enough to drive all life out of the tropics because you are increasing the water and air temperature from an average of 25 to 30, which is very comfortable for many organisms, up to 35 or higher. And then it's becoming physiologically impossible for most organisms to live in that temperature. Secondly, those gases, particularly the sulfur dioxides, they mix with water, giving you sulfuric acid. This is acid rain. So you get acid rain on land that kills the plants, you kill the trees, the forests disappear, the roots are loosened, the soil washes off. We know this happening today. As you cut down forests, you lose the soil, you're left with rock. And the rate of erosion and the exposure is massive. And the oceans become acidified as well. Next one, please. So a lot of the classic work on this episode now is done from the Dolomites, the mountains in the north of Italy. The detail of the dating, the stratigraphy is fantastic. There's some example off to the side. And thanks to that exquisite sort of master section that we have in the Dolomites, with the addition of exact age dating, radiometric dating of volcanic beds and zircons in sandstones, for example, plus magnetostratigraphy, which I've mentioned, means that we have a really quite good geological time scale that we can use to correlate worldwide. Next, please. And that has allowed us to tie together these environmental changes, which Sims and Ruffle had noted, together with the extinctions that I talked about, plus the timing of the eruptions. And it turns out in this country and many other parts of the world where people have looked in detail, that as you can see in figure A at the top right, that there are as many as 3 or 4 individual pulses of the eruption. These are detectable by the carbon isotope and oxygen isotope records, which can be taken worldwide. So everywhere you look, you find the traces of these sharp warming episodes everywhere. So we have independent evidence from all these sections, from Europe, from Asia, from North and South America. Next, please. We're nearly there. And the scaling of the event, as I gave the little caveat at the beginning, there it is marked with a red arrow. So the biggest mass extinction is on the left, the Permian Triassic. And then there's a bunch of others, and the end Cretaceous is the first blue one. The color there is to indicate green is Paleozoic, the more ancient rocks. Blue is Mesozoic. So you can see that the end Cretaceous mass extinction, which is the most famous one, the end of the dinosaurs, the big meteorite, it's not the biggest. And our one is quite a wee way off. So although the one at the end of the Cretaceous equates to maybe 45% of generic loss, ours is 33%. So it's not as big. Next, please. So lots of marine extinctions. I won't say any more about the detail. You can read what it says. It had big effects on reefs and plankton, various other swimming groups like ammonoids and conodonts. And all of these can be timed very closely to the isotope record shown at the bottom, particularly in marine rocks, like in the Dolomites. This kind of quality of the record, you can kind of collect the fossils and collect the samples for isotopic measurements almost millimeter by millimeter. The detail is just amazing. Next, please. And the Carbonate factory, just a word about that. So up to that point, most of the limestone that was being formed on the Earth was happening on the continental shelf to the left there in that little diagram. And then it changed, and that was because most of the limestone was being formed from the skeletons of corals and various other marine creatures that live in shallow waters on the shelf. And that meant that those limestones made of calcium carbonate are the major sink for carbon in the ocean. But they were quite subject to perturbation because it was all in the shallow water, and that meant that if there were storms or major sea level changes, you could perturb the amount of limestone being deposited, and the whole cycle of carbon through the atmosphere, through living things, into the rocks was perturbed. After this event, it moved into deeper water, and you can see on the far right the calcareous pelagic rain, as they call it. So the plankton are in the surface waters all over the ocean, not just over the continental shelves. They're locking up a lot of the carbon into their calcium carbonate shells, calcite shells, and as they die, there's a rain of these little things to the ocean floor, forming, for example, the chalk, the great chalk cliffs of Dover and so on. They're formed in deep water from plankton. So plankton may be small, but there's a hell of a lot of it, so it can produce hundreds of meters of limestone. And that meant ever after this event, the carbon cycle on Earth was massively stabilized, because it doesn't matter if there are major temperature changes, changes in sea level, it affects the shelf. It doesn't necessarily affect the whole cycling of carbon through those skeletons onto the ocean floor. Next, please. I think we're nearly there. Terrestrial extinction, I won't say any more here. There are just tremendous changes. The dinosaurs appeared, plus a whole bunch of modern groups, all indicated in the bottom diagram by those green spindle-like things. You don't need to read all the details, but these are all the different groups that were originating. The extinction event is shown by that sort of gingery stripe going the width of the diagram. Next one, please. And this is the one to finish on. Here we have some early dinosaurs and some other creatures of their day. Here are a variety of plants. This is just to remind you that there were no flowering plants at that time. You've got conifers. Those things are sort of like monkey puzzles in a way. You've got horsetails. You'll recognize those. Seed ferns, a variety of other things. That's what these creatures were eating. This is supposedly at the height of the humid period, lots of rain, lots of vegetation. And then once the temperatures fell, after the eruptions ceased, this belt of heavy rainfall across the hot equatorial region ceased, and the world became very, very dry. And of all these plants, the main beneficiaries were the conifers. They survived. Conifers are known to cope well with dry conditions, whether hot or cold, it doesn't matter. But actually then at that point, a lot of plant-eating animals couldn't cope. And if you imagine subsisting on a diet of pine needles and pine cones, it takes a bit of application to eat those with any relish at all. Thank you. I'll stop at that.
Well, that was fantastic. Do you know, when we go to the recycling centre, we pass by a garden which has a monkey puzzle tree in it. And I always pointed out to my daughter saying, that's a relic from millions of years ago. Yes.
Certainly is. Try eating some in a sandwich and see what you make of it.
Oh, yes, they need some teeth, don't they? And isn't this why, one reason perhaps, why they had to be so big? Because they needed a sort of fermentation vat for the bacteria to break it down for them.
There is a kind of you get some benefits of greater efficiency as you get bigger, definitely.
Mm. You've got a fan here who's
how very nice, thank you.
He's a friend of mine who's bought your book. We have been known to meet up in the Science Museum or the Natural History Museum to go up at the fossils. I'll ask him if he wants to join us on screen, shall I?
And while you're doing that, I can just make a small plug for the book. This is about the end Permian mass extinction, which is the biggest of all extinction events, not the one we're talking about tonight.
What's this? Sorry, your latest book?
Oh, that one that was mentioned there. My latest book is called Dinosaurs Rediscovered, and that's a different subject. That's about the role of science in telling us what we think we know about the paleobiology of dinosaurs, including how we can tell the color of dinosaurs, that kind of thing. But let's not sidetrack.
No, it's just that I would like to have the details of that to put in the comments underneath, so that to promote your work.
That's right.
So somebody who hasn't put their name in is saying, does this relate to the Siberian traps?
Yes. So
he's referring to the methates, isn't he? The
methane hydrates. So
that's the one. Yes.
Yeah. So the Siberian traps were the large igneous province that drove the end Permian mass extinction. That's at 252 million years ago. Our event is 232, so it's 20 million years later. It's not driven by the Siberian traps. At that point, they had gone quiescent, and it's the Wrangellia LIP. But yeah, the model was worked out for the Siberian traps. And the interesting thing we're discovering is, whereas when people started studying mass extinctions in detail, they really looked at the end Cretaceous event, that is at 66. And there the evidence is very strong that this was caused by a meteorite impact. And people tried to generalize that model. They thought, well, maybe we can explain all mass extinctions by meteorite impact. And indeed, if that were the case, then back in the 1990s, people were saying, wow, this could mean that extinctions are happening because of astronomical cycles. There are certain points every 20 or 26 million years where a flurry of asteroids are sent out from the Oort cloud at the edge of the solar system, and they hurtle in and hit planets. But the extraordinary thing is, the best studied mass extinction at the end of the dinosaurs, end of the Cretaceous, that is caused by meteorite impact. All the others, or pretty much all of these others, are certainly these ones around the times we're talking about here, they all seem to follow a common model of volcanic eruption. And that has interesting consequences, because I remember people used to get worried or they would ask a question, what can we learn about the future from looking into the past? And if the extinctions were all caused by meteorite impact, what can you learn from that? I don't know. It would happen again, but how do you protect yourself from it? And I suppose that's in the days of Ronald Reagan and space wars. There were some ideas that NASA could have an enormous gun that would blast an asteroid as it approached the Earth and would sort of save us all. Whereas there is a real relevance, of course, with these volcanic models in the present day, because, of course, if you think about the drivers of warming and acidification, they are these greenhouse gases, and the carbon dioxide, the methane, the water vapor. It doesn't matter whether they come out of a volcano or out of the exhaust pipe of a car or out of a factory. They have the same effect. And so these events of the past give us opportunities to calibrate scaling of events and predictable consequences. So there are kind of predictable consequences. If you put a certain amount of carbon dioxide into the atmosphere, what happens? So already we're predicting, and the predictions are being borne out. Temperature is rising. People predicted that would happen. Guess what? It's happening. And only the very blind would deny that. And of course, we don't want to run an experiment and say, what happens if we raise the amount of carbon dioxide to double what it is now, and then double it again? But we can look at these ancient events, and there have been times when that already happened.
I think the climate change deniers seem to have crawled away into their caves. We haven't heard much from them recently. Hopefully, God. But, I did hear today, I think, that there's some evidence that that methane is coming out of the sea north of Siberia. People are worried that it's the start of the next phase of change, which will be unstoppable.
I think that some of these geological studies have taught us that there's such a thing as a runaway greenhouse, which of course sounds very picturesque if you imagine going to B&Q and something or other in the car park. But what this means is that normally when we think of greenhouse warming, the Earth has ways, the biosphere has ways of mitigating the change. So when Mount St. Helens went off a number of years ago, it pumped all of these gases into the atmosphere. There was a sharp warming event, not a very large one, but sharp and measurable, and it applied over quite a large area of North America. But of course, that excess CO2 was very quickly mopped up by the trees. They photosynthesized, they absorbed the CO2, and within a matter of weeks or months, that blip had gone. And that's the typical kind of homeostasis that we expect, where there is a negative way of dealing with, there is a way of opposing that change. But the worry people have is that if the warming as it's happening now, where we have a polar ice cap, is particularly worrisome, and this is different from the Mesozoic, because there's a great deal of methane locked up both in the deep oceans in the form of methane hydrates, and these are sort of crystalline ice structures held at high pressure and high temperature. And secondly, there's a huge amount of methane in the tundra. In the Triassic, there was no tundra because there was no ice cap. But of course, we have a massive area of tundra across all of Siberia, northern Canada. And of course, as you raise the temperature, even just by a fraction of 1 degree C, it means in summer, more of the tundra melts. And as it melts, out comes the methane. And methane is an organic gas that is produced either from organic plankton falling to the ocean floor, or in the tundra, it's just the roots and plants and stuff. And of course, the more of that, and then it's a runaway greenhouse, because if you warm that by 0.5 degree, it releases a huge amount of methane, which is a very powerful greenhouse gas. That will then immediately begin raising the temperature a bit more. Guess what? More melting, more release, more melting.
Yes.
The runaway
Feedback.
greenhouse.
Positive feedback. Yes.
Exactly.
Is it 20 times or 80 times more of a greenhouse gas than carbon dioxide?
Yes.
Hugely more powerful. Yes. So Tavian is asking, how do you recognize Permian outcrops from rocks from other periods before you decide to look for the kind of fossils you were hoping to find?
The good thing here, Tavian, which it doesn't sound like a great answer, but I'll do my best, is that we're not starting from scratch. When you're a scientist, you do, as Newton says, stand on the shoulders of giants. So we have 200 years of prior work by geologists, including an enormous endeavor by geological surveys in every part of the world to produce geological maps. And it was agreed early on in the history of geology, back around 1840, that everywhere we would use the same geological timescale. It need not have happened that way, because the geological timescale is not like the periodic table of elements in chemistry. Because, of course, those elements in chemistry are real, they're unchangeable, whatever you call them, they have fixed properties. Whereas the geological timescale could have been drawn up in different ways in different places. So as for where we go, I've hunted for Permian fossil reptiles in South Africa, in Russia, in China. I don't have to start from scratch. It's not like just dropping somebody from a helicopter randomly in the middle of China or Russia and just letting you wander about. I look at maps, which isn't a great, it's not actually explaining the fundamentals, because of course those maps had to be produced, but I think I've talked a little bit about those fundamentals earlier. And so those maps, and you'll have seen geological maps of the British Isles. They were first drawn in around 1815. And since 1815, they've been revised and revised, and thousands of geologists have tramped across fields, checking boundaries, checking fossils, checking the ages. So there we are. The glib answer is you look at a map and you get on a bus and you go to the right spot according to the age of rocks that you're looking for. The more fulsome answer is to sort of take you through in that sense of we have the framework of knowledge, we have the big data out there that we can benefit from. And so you don't rewind back to the start again every time a new generation of scientists come along.
Yes, thank heavens for the previous scientists.
Thank heavens.
So do we know which is it's difficult to predict volcanic eruptions, isn't it?
It really is. It's not my special field, but and we have a big volcanology group in Bristol, the head of which, until he retired, was Professor Sparks, which you could say, well, that's obviously the job for him, unless he was an electrician.
Normative determinism, I believe that's called.
That's right.
Would he be interested in coming on my show, I wonder?
I'm sure he could be persuaded. But yes, I think we should be able to detect eruptions in advance. And particularly, for example, in Europe, you look at Italy, because Italy still suffers from active volcanoes which cause havoc. And they have invested huge amounts, they have the best instrumentation, and they still can't predict. And it's like the San Andreas fault as well. All of these movements under the earth, we know they're coming, we know where they're going to be. And we have measuring equipment there, vibration detectors, underground detectors, all kinds of stuff. And so, for example, some of them they sound laughably simple. If you're looking at Vesuvius, and you have shape detectors, cameras essentially, and if Vesuvius starts to bulge, they'll detect that. Even if it's just a millimeter of outward movement, they will detect it. Because simple as it is, that's actually a good marker of when a volcano is going to blow up, is the earth starts to move. But the trouble is it may jerk a little bit, move a little bit, and people say, yeah, this is it. And then nothing. And then nothing. And then it starts up again. And then 10 years later, suddenly, boom, it just goes up. And I wish we could. We know what we ought to do, but we're still not able to do it.
So here's a question about flood basalt. Now, I'm curious to know whether there is any of the what you might call original surface of the Earth still outcropping anywhere. I mean, I understand that most of the middle of Africa is basalt.
Yep.
Is that the original cooling surface of the planet, or which hasn't really eroded away significantly yet, or what?
Yes, I think some of it is. I think there is some truly. So the oldest rock on Earth is supposedly in Greenland, the Isua Formation, ISUA. And I can't remember the date, something like 4.1 or 4.2 billion years. The Earth is supposed to be 4, 5, 6, 7. It's an easy number to remember. 4, 5, 6, 7 million. So you don't get rocks much older than that because the Earth was molten to some extent and so on. And the Isua, I think, does include some sedimentary rocks. So there was already water on the Earth by that time. The Earth. So a lot of basalt, though, is modern or new, because, of course, as the ocean, as the deep ocean, as the plates, the tectonic plates move apart, the ocean, the mid-ocean ridge down the middle of the Atlantic and through the Indian Ocean, etc., etc., they are generating in a symmetrical manner fresh ocean floor at a predictable rate, and this is fresh basalt bubbling up through this fissure, this crack. And this is happening in Africa as it splits apart the Great Rift Valley, and right bang through the middle of Iceland. If you've had the good fortune to visit Iceland, you can have 1 foot on North America and 1 foot on Europe, and a burning furnace deep beneath your trousers. So you better look out. But, so
doesn't sound very tempting.
So yeah, there is original and other part, Africa and Australia. There is really truly ancient Precambrian igneous rock.
Well, we're coming towards the end. I don't like to subject my victims to more than an hour of this torture. So I just wanted to ask you, you mentioned that carbon dating was too short a half-life. It's useful for archaeology, but not for paleontology.
Yes, that's right.
So what isotopes do we use?
I think that the two that are commonly used now are argon-argon. So this is between two isotopes of argon, and uranium-lead. So there's a long sequence of decay from uranium to lead. And those two are currently used by different radiometric dating labs around the world. And I think just so people understand the way this works, of course, each of those labs is a very costly enterprise to operate. And so it's not a trivial thing. Not every university has one, for example. There are only maybe 2 or 3 in each country. They're highly competitive, of course, because you want to be the first to get an important date that tells us something about the origin of life or the dating of one of these big mass extinctions. But they're massively collaborative as well, because one of the backstops in this whole business is you send samples to your competitors to also test. And so that if you are running one of these labs, and the precision, the level of precision, remember accuracy and precision. Yeah. We hope they're accurate, we don't know. But at least the level of precision, the length of that error bar is getting so short. So when I started as a student, and you can speculate when that might have been, the error bars on a lot of geological dates were plus or minus 5%. Now they're typically plus or minus 0.05%. So they've improved by 2 or 3 orders of magnitude. Yeah. And so in dating these extinction events, they may be 232 million years ago, but it's plus or minus 20,000 years.
Yes. Yeah.
That's it's a long time in human terms, but in geological terms, that's a fantastically precise measurement. Yeah. And to achieve that, the mass spectrometers are just so much better than they were. But then it's massively nerve-wracking if you run these, because if you allow your mass spectrometer to go out of calibration, you can get a week's worth of nonsense measurements, and then you say, oh, bloody hell, we better check it back against the standard. Yes. And so the people who run them are very careful. And then, of course, it is competitive. And if your lab is found to be falling short by some other lab, they're not going to keep quiet about it.
No. Well, that's the thing about science, isn't it? Because it is sort of self-correcting. If your evidence doesn't pass muster, then you've lost your job.
That's right. And people, as I say, they don't tell you quietly. They do it in a very public way.
and we've seen it happen. We know of people to whom that has been a fate. Yes. Mike, you have been utterly fantastic. It's been a pleasure listening to you. Thank you very much for coming on the show. I'm just going to do a quick commercial before I play your outro to remind people that next Wednesday, it's a post-mortem of the American election. We're in the hands of Anthony Hook, who was formerly, until we left the European Union, he was formerly an MEP for the Southern England constituency, Southeast constituency. Mike, thank you very much. You've earned yourself a glass of wine or something.
I'll wait for that. Thank you.
Thank you. Bye-bye.
Okay, bye.